Okay, today we're going to talk about another kind of hypothesis testing. There are actually a bunch of different kinds of hypothesis testing that you can do, more than we have time to really cover in this class. So, for example, we are not going to spend time on section 8.4, z-test for a proportion. So that would be if you wanted to test a claim about what proportion or what fraction or what percent of some population falls into some category. Like a claim that over 60% of voters favor a certain candidate, or a claim that less than half of restaurants are offering carry out and delivery, or things like that. Any claim about what fraction or what percentage of some group fits some description. I did on the notes give an example of that and talk a little bit about how that works in case you're curious or in case you ever have to know about that. But we won't spend time on it in this class just because we don't have time for everything. You can also test claims about standard deviations or variances. And for that, you would be doing a chi-square test. So that's related to the chi-square distribution that we looked at when we were doing confidence intervals for variance or standard deviation. So that's another thing that it's in the book. You can look it up if you are curious or need to know about how that works, but we will be skipping over it and not spending any time on it in this class. We will spend time today talking about section 9.1, testing the difference between two means using the z-test. And in the rest of chapter 9, we will skip, but it has to do with other kinds of hypothesis testing. So the kind we're looking at here, section 9.1, testing the difference between two means. So this is where you have two different populations, two different groups of people or things, and you're comparing them. You want to know, is there a difference between how well boys do at a video game and how well girls do? Or is there a difference between two different brands of some product? Or something like that. You're not comparing just one mean to a specific number, you're comparing one mean to a different mean. So in this section, we'll be testing claims comparing the means of two different populations. That means that the null hypothesis will always be that those means are equal to one another. Mu1 equals mu2. The mean for one population is the same as the mean for the other population. And the alternative hypothesis will be either that the means are different, mu1 does not equal mu2, or that mu1 is less than mu2, or that mu1 is greater than mu2. And in the problems that we'll be doing in this section, we will assume that random samples are taken from both populations. The samples are independent of one another. In a minute, I'll come back and say what that means. The standard deviations of both populations are known. So we know the population standard deviation for both groups. If we didn't, we'd have to do a t-test, and we won't cover that, but that is one of the sections that we're not doing. And if the sample sizes are less than 30, the populations must be approximately normally distributed. So I said I'd say more about what it means for the samples to be independent of one another. Let's say, for example, you wanted to test a claim about the average amount of housework done by married women versus married men, done by wives versus husbands. One way to do that would be to randomly select a bunch of married couples. And then in each couple, you compare the number of hours of housework done by the husband to the number of hours done by the wife. That wouldn't be independent samples. Independent samples would just be you get a group of married women, and then you get another group of married men. And they're not necessarily married to each other. There's not any necessary relationship between the men and the women. You just look at the average number of hours of housework done by the women in the group of wives, and you look at the average amount done by the men in the group of husbands. So that's what we mean by the samples being independent of one another. They're not paired up in any way. If they were, that would be a different kind of test that we're not talking about right now. So step 2, compute the test value. The formula for that looks like this. It's this big, sort of complicated looking formula involving 2 different x bars and 2 different mu's and 2 different sigmas and 2 different n's. So in this formula, those 2 different n's, n1 and n2, stand for the sample sizes for your 2 samples. You're comparing 2 different populations, so you need a sample from each population. So you are working with 2 different samples, and they can be different sizes. Like you could have 30 men and 25 women, or whatever. So the 2 n's stand for how many individuals are in your first sample and how many are in your second sample. The x bar 1 and x bar 2 are the sample means for the 2 samples. Those are the averages of whatever it is you're looking at for your first sample and for your second sample. The sigmas, sigma 1 and sigma 2, are the population standard deviations for your 2 populations. And in the problems that we will be doing, this part of the formula where we have the mu1 minus mu2, we're just going to use 0 for that. In all the problems we'll be doing, the hypotheses are just going to compare mu1 to mu2. Either they're the same or they're not the same. And if they are equal to one another, then that means that mu1 minus mu2 is 0. The reason we have that in the formula is because sometimes you want to know not just whether there is a difference, but if there is a difference of a certain amount, if they differ by at least 10 or something like that. And you can see an example or 2 of that in your book if you want to look at it and see what that looks like. But for what we will be doing and for anything that I'll hold you responsible for knowing, this part of the formula is just going to be a 0. So really you're just calculating x bar 1 minus x bar 2 over the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So if you're doing it yourself, calculating things yourself, this is the formula you would be using. There are other ways of doing it. You could use a graphing calculator. And here, the specific calculator function you would use would be 2samp z-test. So you would push the stat button, go to tests, and select 2samp z-test, and then type in all of those numbers. And if you're using the p-value calculator for Excel spreadsheet that I posted on Canvas, said you could download and use for these kinds of problems, there's a tab labeled 2samp z-test that you would go to and type the numbers in there. And it would give you the test value z and also the p-value. So all of these I will demonstrate when we work through some actual examples. So hopefully this will all make sense once we go through some actual examples. Right now I'm just giving you the outline, then we'll come back and work through this and see how it all actually works. So step 3, find the p-value. If you use the formula, that formula to find z, then the way you get the p-value from that is you take that z and you go to table E and you find the p-value the same way we did in section 8.2. If you used one of those other methods, a graphing calculator, the Excel spreadsheet, some other app, then it should tell you what the p-value is. And then steps 4 and 5 work pretty much the same way that they have all along. In step 4, you make the decision to reject or not reject the null hypothesis. And that's just a matter of comparing the p-value to the level of significance alpha. If the p-value is less than alpha, you say reject the null hypothesis. If the p-value is greater than alpha, you say do not reject the null hypothesis. And step 5, summarize the results. You're going to say either there is or there is not enough evidence, depending on whether you did or did not reject the null hypothesis. So you say there is or is not enough evidence to, and then that depends on what the claim actually is. If the claim was the null hypothesis, then that would be about rejecting or not rejecting that null hypothesis. If the claim is the alternative hypothesis, then whatever you said about rejecting or not rejecting the null hypothesis, you're saying about supporting or not supporting the claim. So now that we've gone through the steps and I've tried to explain how they work, now let's work through some examples. So I'm going to end this part of the video here and come back with part 2 where we actually work through a couple examples. And hopefully then you should see how this all works and it should start to make sense. See you then.